Okay, this is going to be your chi-square goodness of fit part 2 video. This is where we're going to go over what you have to do when you run a chi-square test to test the hypothesis and get full credit for it. The first thing you're going to have to do is identify the test by name or formula. But when we're going to do a chi-square goodness of fit test, we talked about a minute ago, we have one sample, a categorical variable with more than 2 categories. So we're going to say here we have, back to the same example we did in part 1 video, we have one sample, more than 2 categories, so we're going to do a chi-squared goodness of fit test. The Greek letter chi, you can write like that, goodness of fit test. You have to name the test. The next thing we can do, we're going to check the conditions for inference. Sometimes in FRQ, they'll tell you the conditions of inference are met. To assume that, you don't have to check the conditions if they tell you that the assumption that the conditions are met. Otherwise, you need to check the conditions. The first thing we need to do is make sure that we have a random sample, just like all of our other tests. Like we did in our other test, we need to make sure that the sample size, N, is less than or equal to 10% of the population size. In this case, we have a random sample of 60 students. We would have to assume or be sure that there are at least 600 students in the school so that we have a random sample of less than or equal to 10% of the population. Now, before we had to fit a condition, had to satisfy a condition that guaranteed the sample distribution would be normal or approximately normal. And here, we know the chi-square distribution is not likely to be normal, but we still need sufficient sample size. This is how we're going to make sure this, and I'll explain this in a few moments. All right, we need all expected counts to be greater than or equal to 5. That's a condition that takes the place of our, to make sure we have a sufficient sample size. Here, if you had one of these categories where you expected the value to be less than 5, even if it was 4, then we wouldn't be able to run this test. It doesn't matter what our observations are, what our observed data is. If this was a 0, a 20, a 20, a 20, we could still run the test as long as we had all expected counts greater than or equal to 5. Those are the conditions to run a chi-square goodness of fit test. Next thing we'll do is we'll write our hypotheses. Just like in the test we've done before, we have a null hypothesis and we have an alternative hypothesis. For a chi-square goodness of fit test, we are going to always write the null hypothesis as the distribution is proportioned as we expected. A lot of times, it will be that every category has an equal proportion, okay? So all the proportions in the categories, in this case, all the classes are 25% of the total distribution. That would be our null hypothesis. Sometimes you'll have a distribution where they may compare this year's freshman class, sophomore class, junior, seniors distribution to some previous year or a historical distribution. A lot of times, freshman class is larger than sophomores, larger than juniors, is larger than the seniors because some people drop out, some people move on. So there may be a previous distribution, but you expect it to fit some previous or some presumed pattern, some presumed distribution where the proportions are going to match. So here, you're going to say that all of the categories fit some presumed proportion. Categories, proportions. Some presumed or assumed distribution. You need it in context though, not just general. If I was writing a null hypothesis for this test, I would say that there are 25%, there are equal percentage, an equal proportion of freshmen, sophomores, juniors, and seniors at Fred's High School. The alternate hypothesis, the alternative hypothesis, is that at least one category, this is in context again, category, plural, differs from the proportion in H0. We need this in context. So my alternative hypothesis here would probably be that at least one class has a larger or smaller proportion than the others. That's how you write the hypotheses for a chi-square goodness of fit test. The next thing is your calculations. When you do this part, you have to show, be sure you write a list, table, however you do it, but distinguish between your observed counts and your expected counts. For a chi-square goodness of fit test, I would make a table or a list of both separate. Label them clearly. One thing we need to make sure, I made this a nice pretty 60 divided into 4 categories so that each one had 15. If this had been 50, it wouldn't have divided so pretty, and we would have had 12.5, 12.5, 12.5, 12.5 in our expected counts. It's okay to have decimals in your expected counts. When you run a calculator test, if you have decimals in your expected counts, you're good. If you put decimals in your observed data, where the test is expecting counts, where you're counting 1, 2, 3, you can't have 1.5 people as freshmen, okay? You can't have decimals in your observed data on a chi-square test. It'll throw you an error on the calculator if you do that. So we have to show our observed counts and our expected counts. We're going to identify our degrees of freedom for the test. For a chi-square goodness of fit test, this is the number of categories minus 1. I told you in the last video that degrees of freedom for this test would be 3, because I have 4 categories minus 1. So degrees of freedom, you're going to show that in your calculations. We're going to put our chi-square test statistic. The calculator will give you that, but I also showed you how to calculate that in the last video. Remember, observed minus expected squared divided by the expected, plus observed minus the expected squared divided by the expected, so on and so forth. We're going to show that, and then I showed you in the last video also, well, let's put this again, sum of the observed minus the expected values in each category squared divided by the expected in that category. And then we're going to make sure we identify our p-value and our alpha. P-value is going to come from the calculator. And our alpha, remember, is our significance level. How willing we are to make a type 1 error. Usually 0.01, 0.05, or 0.10. We're going to make sure this is a significance level of the test. And this is the probability of getting a test statistic as extreme or more extreme than the one we get in our sample, if our null hypothesis is true. Test statistic as extreme or more statistic, as extreme or more extreme as ours, if the null is true. We need to show all those in our calculations. And finally, you should be used to this by now after all the hypothesis tests we've done, we are going to our conclusion and context. We have two different possibilities here. If your p-value is less than alpha, then we're going to state because, and we're going to plug in our p-value here, is less than our alpha, whatever that is, for our test that we're running, because our p-value is less than alpha. The evidence suggests, the evidence suggests the alternate hypothesis in context. Here, in our test that we run here, if this is the case, if this is what we find, we would say at least one of freshman, sophomore, junior, or senior's proportion isn't equal to 0.25. There's at least one class that's larger or smaller than the other classes. And we reject H0. That's the conclusion in context if the p-value is less than alpha. If the p-value is greater than alpha, then because, again, we're going to plug in our p-value. If you don't link this conclusion to the p-value in alpha, you're not going to get credit for it. Because the p-value is greater than alpha, whatever our alpha is for our test, there is insufficient evidence to suggest HA in context. Whatever our alternate is in context. And we fail to reject H0. We don't have enough evidence to say the null is false, to suggest the null is false. And those are the criteria for full credit. In the next video, we'll work through this example, doing everything like we would if this was just the example we were given.